In this video, we'll revisit Scheme's general rule of evaluation to see how it applies to compound procedures. So Scheme's general rule is how it determines the meaning or the value of some expressions, and it has two main steps. First, we need to evaluate all of the sub-expressions of the combination that we're given, and then we need to apply the value of the procedure to the value of each of the arguments. Let's look at a concrete example here. So if I wanted to, for example, evaluate the combination or the expression 1 plus 2 times 3. First things first, I need to evaluate all of the sub-expressions. So I'd have to evaluate the symbol plus, I'd have to evaluate the symbol 1, and I'd have to evaluate this combination of symbols times 2 and 3. Right. So in order to evaluate these things, the rules work a bit different for each of them actually. This one here is a symbol. It's essentially a variable name or a symbolic abstraction. And we can ask what the value of that symbol is, and the value is the procedure object itself, the thing that can do addition. This is sort of the underlying mechanics built into Scheme, which ultimately goes to the hardware of the system itself. So this is procedure plus. Now, in order to evaluate 1, well, that's just an integer, so it's self-evaluating. We already know its value. It's a 1. In order to evaluate times 2, 3, this combination, well, we need to recursively apply Scheme's general rule of evaluation to determine its meaning. So we'd say, what is the value of the sub-expressions? So we say eval times, eval 2, and eval 3. Now we've seen how all these work. We have symbols. They're just the value that they point to. So if we had a symbol x, for example, it would just be the value that we defined it to be. With built-in symbols, we just use the value that they've been built with. Integers are, again, self-evaluating, so we know 2 and 3. Now, once we have the value of all of the sub-expressions in that combination, right, we know procedure 2 and 3, then we're ready to do the apply step. So we'd say apply, and I'll write out the whole thing this time, the procedure, well, that should be a multiplication procedure. Procedure times, sorry. Okay. We'll apply that procedure to the arguments 2 and 3. Okay, and the apply step is what does the actual work. It's what takes these pieces, this procedure object and the arguments to it, and turns it into some sort of result. In this case, by multiplying 2 and 3 to give us 6. And now the answer to this application, to this apply multiplication to 2 and 3, that answer is the answer to the entire eval question that we had here. So the value of times 2, 3 is 6. And the answer to, and what we have now is the value of all of the sub-expressions of the top level combination. So we had plus 1 and this times 2, 3. Now we have procedure plus, the value 1, and the value 6. So what we're ready to do is apply those together to get our final answer. So we'd say apply, I'm just going to write times for short, to the arguments 1 and 6. And this will yield 7. Oh, sorry, that should be a plus, not a times. Right, we have the procedure plus 1 and 6. So we apply plus to 1 and 6, that'll give us 7, and then the entire answer here, then put it out here so we know it came later, was 7. Okay, so that's the basic idea of Scheme's general rule of evaluation, or at least as it applies to primitive operations, arithmetic steps. So if we have primitive procedures, the apply step, essentially we just assume the interpreter handles the specifics of it, right? If we want to say what's the combination that brings 1 and 6 together, what is this step here? Well, the system knows how to do addition, we can just ignore it, okay? But not everything can be built directly into the interpreter. That's why we're creating our own procedures. So if we have a user-defined procedure, or a compound procedure as we called it, apply takes on a different meaning. So the apply operation, or the apply step, means we take the values of the arguments and we substitute those into the formal parameters, the symbols inside our procedure. We do that substitution everywhere throughout the body of that procedure. Then once we've made that substitution, we can then call the evaluate function again to evaluate the body of the procedure with those symbols in place. So let's see an example of that, because that will make more sense. So let's say we wanted to let's create a procedure first. Let's say define double x to be plus xx, like in the notes. And let's say what will happen if we eval double 5. So So in order to evaluate double 5, we follow the general rule of evaluation, which says evaluate the sub-expressions, which is eval double and eval 5. Now the value of double, if we want to see what that is, we can run this and type in double. And that's again just essentially a symbolic abstraction. We put the name double in place of this procedure object. So if we want to know what the value of that symbol is, it's just the thing that's bound to it. So procedure double. And 5 is just an integer, so we know its value is 5. Now we're ready to do the apply step. So we say apply double, I'll just type the short version, to the argument 5. But what does the apply step mean here? Obviously, all of the possible procedures a user could create can't be built into the system itself, so we have to have a rigorous system for going through and being able to determine what the meaning of some procedure is, regardless what that procedure specifically is. So the general rule of evaluation says we first substitute each formal parameter into its, by its corresponding argument. So we have the argument 5 goes into the formal parameter x, and we do that everywhere throughout the body of the procedure. And then it says we evaluate the body of the procedure with that substitution in place. So essentially, in this drawing here, we'd have, in order to apply double to 5, we say eval plus xx, the body of that procedure, but with the substitution in place, so plus 5, 5. Okay? And this now goes back to the general rule as we've seen it before. So in order to evaluate that, we have to evaluate the sub-expressions. So we get eval plus, eval 5, and eval 5 again. And then we can apply plus to the arguments 5 and 5 to yield 10, which will be the result both of this application, but that's also the answer to this eval step, which is also the answer to this apply step, which is also the answer to this eval step here. So the final answer then comes out as 10. Okay. So that's the idea of the general rule of evaluation. It's important to notice that two things here. First off, eval and apply form this mutually recursive process, right? Eval calls apply in order to determine the value of some sort of procedure application. So apply is some function that can determine how to combine some procedure symbol with some argument symbols. So it's a procedure that determines that in a general way. And then we have the eval procedure, which figures out the meaning of specific values, like integers and pluses, and as well determines when it needs to break down something into sub-expressions in order to do the apply step. So eval calls apply, and apply calls eval, right? Apply says in order to apply double to 5, we had to call eval, which then called apply. So we have this mutually recursive process between eval and apply, hence the weird symbol here. Also important to notice, the interpreter itself, which is following this eval apply process, is just a program, right? We have some input, which in this case would be our expressions, the things that we're typing, like double 5 and all of these, which we'll see how that gets interpreted later on in the course. So our input is just the expressions that we're typing, and the output is then the value of those expressions. So the interpreter here is just eval apply, and it's just a program like any other. Now, if we had to type this out every time we wanted to figure out the meaning of some expression, if we wanted to manually solve these rather than typing them into an interpreter, it would get very exhaustive if we had to type eval apply every single time in order to follow this system. So the substitution model for procedure application is sort of a shorthand for doing this. It represents the meaning of procedure application in a simplified way. So let's walk through this same example, double 5, and we'll see how it works in the substitution model. So if I wanted to evaluate double 5, well, the substitution model, it follows the same rules, we just type less essentially. So that says we substitute our argument into the body of this procedure, but we still have to walk through the general rule in our mind. So the value of double is the procedure, the value of 5 is self-evaluating, so that's pretty simple, and we do the application. So the next step in this is take the body of that procedure, so plus xx, and it's called the substitution model because we substitute our arguments into the body of the procedure. And then we can reduce with arithmetic as we normally would, so plus 5 and 5 just gives us the value 10. So the substitution model, it's not a complete model of the interpreter, it's a sort of a mental model of functional computation. It's not the real thing. We'll see situations where it fails later on in the course. But it does give us accurate results. If we have purely functional programs or purely functional expressions, we can manually walk through them with the substitution model to determine their value. But let's see the substitution model in a bit more involved light here. Let's create a couple more functions first. So I think we had these before, but let's create them again. Define square x to be times xx, and define sum of squares. I'm just going to type SOS instead of typing the full word. X and y, and that was the sum of square x and square y. Okay. Yeah, let's go one more step here. A function f of a, which does sum of squares, SOS, of plus a1 and times a2. All right. So all three of these, I believe we created these in a previous video, but let's see how they apply to the substitution model. So our substitution model would be, we start with some expression that we want to evaluate. So I'll say, what is the value of f at 5? And I could obviously just run the code and see what it is, but to manually walk through will inform how the interpreter does all of those steps. Right, so the first step with f of 5, if we want to follow the general rule, we say evaluate the sub-expressions. So the value of f, let's run our code here. The value of f here is the procedure f, and the value of 5 is just the value 5. So we know those already. And then we go to the apply step, which says apply this procedure f to the argument 5. Now to do the apply step, we take the body of that procedure. I'm actually going to put all these in comments so we don't get a bunch of spam here. So we take the body of that procedure, and everywhere where there was the parameter, in this case the letter a, we take the argument, in this case the number 5. So we have plus 5, 1, and times 5, 2. And then we walk through our general rule again. So the general rule says evaluate the sub-expressions. So this is a procedure. It's a compound procedure, so it has a body that we'll deal with when we do the substitution. But these things are not ready for application. We can't apply a procedure to this combination. It has to be a value. So before we can apply SOS to these two sub-expressions, we need their values. So we'll walk through the substitution model, which for arithmetic is pretty straightforward. For plus 5, 1, we can just turn that into a 6. And for times 5, 2, we can turn that into a 10. Now, it's important to point out here, these two sub-expressions can be evaluated in any order, right? In the substitution model here, I've said let's just do them at the same time, because if we had a parallel machine, technically we could. If we wanted, we could have written it down like this, SOS plus 5, 1, and 10, or we could have done it the other way, where we had 6 and we hadn't yet evaluated this. This one perhaps makes more sense. Typically speaking, if we have a serial machine, a single processor going through, it has to do one before the other because it can only do one thing at a time. But the choice of which one it does is irrelevant. And indeed, they can be run at the same time if we had the hardware to support it. Right. So the substitution model, as far as substitution model is concerned, we can just evaluate at the same time, save ourselves some typing. Okay, so now we have the procedure SOS, which again we could type out in this long form, but it's just a bit simpler to keep in its short name. And the two values, 6 and 10. So we apply that procedure to these things, which means take the body of that procedure, copy, replace, and everywhere where we have an x, we replace it with a 6, and everywhere we have a y, we replace it with a 10. So 1 each this time, 6 and 10. Okay, and again, so we have plus, which is just addition, but we can't apply plus to a combination. We have to first find the values of those sub-expressions. So we have plus, and we have to figure out what is square 6. So square 6 has its own body, so times xx, where x is 6. Now again, if you want, you can go one step at a time and solve out all of square 6, and indeed the interpreter, I believe, will just do that by default. It's not going to randomly move back and forth. It goes left to right. But for the substitution model, we can sort of short form it and do both of these on the same line. Because again, there's no crossover. They're independent sub-expressions. All right, and so before we get to plus, again, plus is dependent on the values of these sub-expressions, so we have to do those before we can do plus, so there is an order there. But for example, finding out the value of 6 times 6 is not dependent on the value of 10 times 10. So we can get those at the same time in our substitution model, 36 and 100, and then finally 136. So that's the substitution model. We take the input expression that needs to be evaluated, and we substitute the arguments into the parameters in the body of the expression over and over and over again until we arrive at a singular value. And that's exactly what the eval-apply process inside the scheme interpreter does when we ask it, what is the value of f at 5? All right. One other thing to point out about the substitution model is every stage along the path of the substitution model is a perfectly valid expression, and indeed it's an expression that has the exact same value. So if I uncomment all of them, we get a whole bunch of 136s, one for each line in our substitution model. So for example, on an assignment or a test, or maybe not so much a test if it's, well, I guess they're online now. So on an assignment or a test, if you want to make sure that your substitution model looks good, you can uncomment everything, and you should get the same answer on every line. If not, then perhaps you've had a typo somewhere. All right, one last thing for this video, special forms. So the eval-apply, or the general rule, is the core of the interpreter, but not every expression can be evaluated in this way. And this brings us to the notion of special forms, which are any expression that is not evaluated in the usual way. So any combination that does not fit into those standard eval-apply steps, we consider to be a special form. So for example, define is a special form. In fact, it's a special form that we couldn't live without. So define, for example, let's type in define some new variable to the value 3. So we saw in a previous video, this creates a variable called newvar and has the value 3, a binding between this symbol and this integer. But this expression define does not fit into the standard eval-apply process. So what would happen if we tried to walk through this using the general rule? So first we'd say, well, we evaluate the sub-expression. So what's the value of define? Well, if define were just a regular procedure, it would work, but technically it's not. It's bad syntax. So this is one way you can determine that define is not a standard procedure because it doesn't have a value, right? When we ask what's the value of double or plus, it tells us, well, here's its value. It's this expression. It's this procedure object. But define is a special form. It can't be handled in the standard way. So it's actually a command to the scheme interpreter to handle this differently. But even if define were just a regular procedure, we continue on evaluating the other sub-expressions, and we say, what's the value of newvar? Well, we haven't yet created newvar because that was the whole point of creating, or for typing this expression. So we get to the second sub-expression, and it doesn't make any sense. We can't evaluate this sub-expression using the standard rules because that would break everything. So define needs to be a special form. So again, the special form is any combination that doesn't follow the standard eval-apply rule, something that either can't or just perhaps for optimization reasons doesn't. That is considered a special form. Right, so the rules for define, since it is a special form, it doesn't follow these steps. Basically what define does is it says take the first argument as a symbol without evaluating it, so newvar is just this symbol, newvar, and then evaluate the next argument. So instead of 3 here, we could have had +1, 2, for example, and the binding would still be between this symbol and the integer 3. It would be the result of the second sub-expression, or I guess, sorry, the third sub-expression. The second argument. Right, and then it creates a binding between those two things. So it says anytime you refer to this value, we'll give you back the value 3. So we've seen a few other special forms. We'll see more as we go forward. But we have seen one already beyond just define, not just define for procedures. That's also considered a special form as well. This keyword define here, which does a slightly different thing, we'll see later on is doing the exact same thing, just in a different way, sort of a syntactic sugar. But we've seen other special forms. We've seen the ands and or operations. Let's do this down here. Let's run this and here. So for example, if I said and false and bad var was the example we saw last time. If we followed the standard rules of evaluation, the scheme's general rule here, and would be a procedure, which it may or may not be. Hashtag F is fine, that's just the value for false, but bad var doesn't exist, right? That's a variable that we haven't created, so trying to evaluate it would throw an error, right? I'll actually just demonstrate that. So our code still works, but if we typed in bad var, that gives us an error. And itself, if we type it in, you can see it's not considered a procedure object. So that's your first clue that it's a special form, but it also, the reason it's a special form is not because it has to be. You could easily conceive of an AND operation that evaluates both of its sub-expressions and then determines the truth of it. But it's just done this way for optimization. It's faster to determine that because this is false, the entire thing is false, so don't evaluate this other expression. Sort of a lazy evaluation of the expression just to save on computer cycles. All right, so again, special forms are anything that don't follow the evaluation rules, and the evaluation rules are evaluate all the sub-expressions before applying the procedure to the values of the sub-expressions. So we evaluate everything, and then we combine. And things that can't or don't follow that rule are called special forms. And we'll see more as we go forward, and that is the end of this video. In the next video, we'll talk about evaluation strategies, that is to say, other general rules that exist. And I will see you then.